Welcome to another math video. In this one, we're going to finish up section 6-4, dealing with vectors and dot products. And we're going to start here with a new vocab word, orthogonal vectors. And if we see below here, before we read the definition, the terms orthogonal and perpendicular have essentially the same meaning, that they meet at right angles. Even though the angle between a zero vector and another is not defined, it can blah, 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 blah. So back up to the definition. The vectors u and v are orthogonal, or at 90-degree angles, if and only if their dot product is equal to 0. So in the last video, we saw how to find dot products. If we happen to run across two vectors with a 0 dot product, that means they exist at a right angle. So let's see what we got here. Determine whether u and v here are orthogonal. So what we're going to do is find u dot v, 6-4. So we multiply the first two things together, and we get 12. And we add to that the second two things multiplied together, negative 12. 12 plus negative 12 is equal to 0. So these, if we were to graph them in the plane, and it's not that hard to do, well, that's pretty terrible. That's a little better. 2 comma negative 3 would be a vector that looks like this. So that would be u. And then we have 6-4, 6 comma 4, 3, 4, 5, 6, 1, 2, 3, 4. Now, granted, my picture's not going to be that great, but yeah, it kind of looks like those two there would meet together at a right angle. So they are orthogonal due to the 0 dot product. All right, finding vector components. We've seen applications where you can add two vectors to produce another vector, the resultant vector. Many applications in physics or engineering pose the reverse problem, decomposing a given vector into the sum of two vector components. If we consider a boat going down an inclined ramp, as we see here in the figure, the force F due to gravity pulls the boat downward down the ramp and against the ramp. So here's F going straight down. This has two effects on the boat. It pulls us down the ramp, and it also pushes us against the ramp, the gravity of the boat, or the weight of the boat. These two orthogonal forces are W1 and W2. These two components are vector components of vector F. That is, vector F is made by adding these two components together. The negative of W1 represents the force needed to keep the boat from rolling down the ramp, so here's W1. If we reverse it, the arrow would be pointing the other way, and that's the force needed to keep the boat from rolling down the ramp. W2 represents the force the tires must be able to withstand against the ramp. W2 is sort of the weight down here, so the tires are taking that pressure. Blah, blah. A procedure for finding these components, W1 and W2, is described below. So, vector components, we let u and b, they're both non-zero vectors, such that u we can break down into its two components. W1 and W2 are orthogonal, and W1 is parallel to, or maybe just a scalar multiple of, vector v. The vectors components 1 and 2, they are vector components of vector u. The vector component 1 is a projection of vector u onto vector v, and it's denoted like this. Vector component 1 is the projection of u onto v. The second vector component is given by, we just subtract vector component 1 from the original vector u. And then down below that, we talk a little bit more about these projections of one vector onto another. Let u and b be non-zero vectors. The projection of one vector onto the other is given by this. And I'm just going to rewrite it a little bit bigger. The projection of u onto v is equal to this. Now notice the numerator is a dot product, u dot v in the numerator, and downstairs we have vector v's magnitude quantity squared. Another way to think about that would just be we're going to dot v with itself, because doing it once would be the magnitude. If we do it again, it would be the magnitude squared. And then what's in these red parentheses here, that will turn into a number, usually a fraction, and then we will distribute that over vector v. Now it's a little confusing with all the u's and v's, but let's just jump into a problem and see if things can get cleared up a little bit by just doing one. So we got example 5 here. Find the projection of u onto v, and then write u as a sum of two orthogonal vectors, one of which is our projection. So here we got a picture. We got our vector v here, 6, 2, u down here, 3, 5. We want to find these component pieces, w1 and w2. Let's get this picture out of the way so we got a little more room to write. So vector component 1 is equal to the projection of u onto v. And I'm just going to rewrite what I had on the previous slide. So upstairs we'll have u dot v. Downstairs we'll have v dotted with itself. And then we will distribute that over vector v. So let's see here. I'm just going to make this a little bigger. I'm going to underline my two vectors. So here's vector u, here's vector v, and the first thing we're going to do is dot those for our numerator. So u dot v, we would multiply 3 times 6, that's 18, plus negative 5 times 2 is a negative 10, and so we'll have up there an 18 minus 10. Down in the denominator, we're going to dot v with itself. So here's vector v. So first term is a 6, so we'll do 6 times 6. That's 36. Plus, we will multiply the 2 by itself. 2 times 2 is 4. So there's our fraction. And then we were going to distribute that across vector v. So let's find our fraction first. Numerator 18 minus 10 is 8. Divided by 36 over 4 is 40. And before we go any farther, we can reduce that down. 88 over 40, they're both divisible by 8. So that would be, what, 1/5? Yeah, 1/5. So 8/40ths, we can get rid of that and replace it with a 1/5. And now we're going to distribute that across vector v. Vector v is 6, 2. 6, 2. So vector component 1 is equal to the vector 6/5, 2/5. Okay, so I'm going to clear this out and put this up here for safekeeping. Now I'm going to flick back to this. Oops, get out of there. Vector component 2 is vector u minus the component that we just found. So let's go back to this problem. I'll switch to red ink. Vector component 2 is equal to vector u minus vector component 1. So vector u, that is 3, negative 5. And we're going to subtract what we just found up here, vector component 1, 6/5, 2/5. Now, because what we have here is fractions, I'm going to take a trip back to the first vector here, u, and I'm going to put that in terms of fifths. So 3 would be 15/5. 5 would be, or negative 5 would be negative 25/5. So this will make it a little bit easier to do the subtraction. And I can just put this right up here. And now we're going to subtract. Get my little brackets ready there. 15/5 minus 6/5 is 9/5, comma. Negative 25/5 minus 2/5 is negative 27/5. So I'm going to, get rid of this. And what we found here is vector component 2. Oops, drop my comma. There we go. And now if I go back up here, and then write u as the sum of the two orthogonal vectors, one which is the projection. Oops. So what we're going to do, u is equal to the two, that's supposed to be equals, the two components added together, w1 plus w2. So let's see, oh, well, I'm not going to rewrite them down here. I guess we can just do it like this. I've got them lined up. We've got 6/5 plus 9/5, that is 15/5, comma, 2/5 plus a negative 27/5 would be negative 25/5. And then if we look at the component here, 15 divided by 5, well, that's just a 3, comma, negative 25 divided by 5 is negative 5. And that's back to where we started. Vector u. All right. That was a good one. Let's see. Determine whether these vectors are orthogonal. That won't be too bad. And then finding this projection down here. That shouldn't be too bad either. So let's see here. So we're going to find out if these are orthogonal. We're just going to do a dot product. So u dot v equals, we take 6 times negative a third. That is, get back there, negative 6/3. And then we're going to add to that 10 times 1/5. 10 times 1/5 is 10/5. And let's simplify here. Negative 6/3, that's a negative 2, plus 10 divided by 5 is 2. If we add those together, we do get 0. So we have determined that those two given vectors are, in fact, orthogonal. Okay, and yep, now for the grand finale. So here's our, get out of there, our projection. Let's see. So vector component 1, that is our projection of u onto v. So remember, up in the numerator, we're going to do u dot v. Denominator is v dotted with itself. And then we will distribute that over vector v. Let me enlarge my vectors a little bit here. There we go. And I'll underline them in red. So our numerator is u dot v, so we multiply the 3 times the 8, 24, plus 4 times 2 is 8. There's our numerator. In the denominator, we will dot v with itself, so we do 8 times 8, plus 2 times 2, 4. And that will be a fraction that we will distribute across vector u, which is, over vector v, which is 8, 2. So let's see here, 24 plus 8, that's 32. Over 64 plus 4, that is 68. And before we distribute that over the vector, let's reduce it. I notice that they're both even, so I can chop the numerator in half, and I can chop the denominator in half. And they're even again, so I can chop the numerator in half again. Half of the denominator would be 17, and that looks like as far as we can reduce it. So we are going to distribute that scalar 817 over the vector 8, 2. So let's see what we get there. 64 17ths, comma 16 17ths. So that is our vector component 1. I guess I'll squeeze it up here. 64 over 17, comma 16 over 17. Now to find vector component 2, we're going to take u and subtract this w1 from it. And notice here our denominators are 17, and vector u is 3, 4. So let's turn those into fractions with denominators 17. See, that would be a 51 17ths. And then for 4 times 17 is 68. That becomes 68 17ths. And from that, we're going to subtract the vector component 1 that we found previously. 64 17ths, comma 16 17ths. And I made these just a little too big. Let me shrink them just a bit. There we go. So now we're just going to subtract each piece. Let's see what we got here. 51 minus 64. That's a negative 13 over 17, comma. 68 minus 16 is 52 17ths. And there we go. Now I'm trying to see, when we did this problem, they wanted us to show that it worked. Right, U as a sum. Actually, let's just do it even if they didn't ask us to. So now if we add these two vectors, we should get back to where we started. So I'll put a plus sign in between them. And let's see, if we do add 64 plus a negative 13, that'll take us to 51 over 17, comma. 16 minus 52, or no, 16 plus 52, what am I doing? We're adding here. That would be 68 over 17. And if we divide, 51 divided by 17 is equal to 3, comma 68 divided by 17 is equal to 4. So we're back there to, where did that go? Vector u, 3 comma 4. All right, I believe that's it for this video. We'll do some practice problems in class, and the assignment will be on WebAssign.
Oh, poop.